Approximately 4.6 billion years ago, a solar nebula existed. The solar nebula was a swirling cloud composed of gas and dust. This nebula occupied the space where our solar system would eventually form. Gravity initiated the collapse of the nebula, pulling particles inward. As the nebula contracted, its rotation speed increased significantly. The core of the nebula experienced escalating pressure and temperature, leading to nuclear fusion and the birth of the Sunday. The Sun's core reaches 15 million degrees Celsius, facilitating nuclear fusion. Hydrogen atoms fuse into helium in the core, releasing vast amounts of energy. The radiative zone surrounds the core, where energy diffuses slowly outward over millions of years. The convective zone features hot plasma rising and cool plasma sinking, transferring energy to the surface. The Sun's visible surface is called the photosphere. The photosphere has a temperature of approximately 5,500 degrees Celsius. Above the photosphere lie the chromosphere and the corona. These layers constitute the Sun's outer atmosphere. The corona's temperature reaches millions of degrees, far exceeding the photosphere. The extreme heat of the corona is an ongoing area of scientific research. Nuclear fusion occurs in the Sun's core due to extreme pressure and heat. Hydrogen atoms fuse together to form helium during nuclear fusion. A small amount of mass is converted into a large amount of energy. This process follows Einstein's mass-energy equivalence principle, E equals mc squared. Energy generated in the Sun's core traverses the radiative zone. Within this zone, energy particles collide with dense plasma, causing them to bounce around. This process can delay the energy's journey to the Sun's surface by thousands or millions of years. Upon reaching the surface, energy is emitted as photons, traveling at the speed of light. Sunlight reaches Earth in approximately 8 minutes and 20 seconds. Sunlight delivers visible light, ultraviolet radiation, and infrared radiation to Earth. The energy from sunlight drives Earth's climate system. Sunlight powers photosynthesis in plants, which is essential for life on Earth. Sunlight contributes to the solar wind, which interacts with Earth's magnetic field to create auroras. Sunspots are dark regions that appear on the Sun's surface. These spots are a result of intense magnetic activity within the Sunday. The strong magnetic fields inhibit the normal convection process. This inhibition leads to a localized reduction in temperature. Sunspots are cooler than their surrounding areas, causing them to appear darker. The number and size of sunspots fluctuate in an approximate 11-year cycle, known as the solar cycle. Solar flares are sudden bursts of electromagnetic radiation from the Sunday. These flares are significantly more powerful than volcanic eruptions on Earth. Coronal mass ejections, CMEs, are massive expulsions of plasma from the Sun's corona. CMEs also involve the ejection of magnetic fields. These ejections travel at millions of kilometers per hour into space. Both solar flares and CMEs are significant solar phenomena with potential impacts on space weather. A CME impacting Earth's magnetosphere can induce geomagnetic storms. Geomagnetic storms can disrupt power grids, GPS signals, satellites, and radio communications. The interaction also creates auroras, visible near the Earth's poles. Scientists monitor solar activity to forecast and mitigate the effects of CMEs. The Sun is currently a middle-aged star in its life cycle. It has existed for approximately 4.6 billion years. The Sun is fueled by hydrogen, which it will continue to burn for another 5 billion years. Over time, the Sun's brightness and temperature will gradually increase. This increase will lead to significant environmental changes within the solar system. These changes are a natural part of the Sun's stellar evolution. As the Sun ages, it will gradually increase its heat output. This increase in solar radiation will significantly impact Earth's environment. Approximately a billion years from now, Earth's oceans will begin to evaporate due to this increased heat. The evaporation of oceans will drastically reduce Earth's habitability. Life on Earth will face the challenge of adapting to these new conditions or migrating. This illustrates the profound, long-term consequences of stellar evolution on planetary environments. The Sun will transition into a red giant phase upon exhausting its hydrogen fuel. During this phase, the Sun will dramatically expand in size. The expansion will cause the Sun to engulf Mercury and Venus. Earth may also be engulfed by the expanding Sunday. The Sun will fuse helium into heavier elements like carbon and oxygen.